Jim, thank you very much. And Brahm, thank you for your perspectives and importantly, your long-standing leadership with organizations such as Institution for Biological Engineers. So much appreciated. Your reflections were right on. And as is common with events like this, jam-packed agenda, different perspectives, overlapping narratives. When the events start off, you usually see some chaotic behavior creeping into the agenda, and something happens on the way, and the skillful moderators such as Chuck Rice, Paul Singh, and Sue Noakes create an emergent property and bring us back on time. So their expertise is much appreciated. As we get into the keynote segment of today's program, I want to prepare you to take a step back. It's going to be a meta conversation with Julio Utino. He's going to take us on a whirlwind tour, a treatment of complexity based on his own work and based on his life perspectives and experiences, really touching on some fundamental questions that really surround even the concept of systems. How do you study something if you don't exactly know what it is? And Julio is going to take us on that journey of thoughts with us. Just a bit of introduction. Julio Utino grew up in Argentina with a dual citizenship, I would say, intellectually speaking, in physical sciences and visual arts. He's a chemical engineer by background. He's the dean of the McCormick School of Engineering and Applied Sciences at Northwestern University. He is a member of both the American Academy of Arts and Sciences and the National Academy of Engineering. And in 2017, he received the Bernard Gordon Prize for Innovation in Engineering Education from NAE, which is the nation's highest award for engineering education. Julio, we are really delighted that you're here with us, but let me also take a moment to thank our contributors to this program before we turn it over to you. Importantly, the Agricultural and Applied Economics Association, American Society for Agricultural and Biological Engineers, American Society of Agronomy, Crop Science Society of America, Institute of Biological Engineering, and the Science Society of America. Julio, over to you. I'll be back online in 30 minutes or so. If you could please unmute yourself, please.
Guru, thank you so much for that introduction, and I'm delighted to be here to give some ideas, which many of them will be very simple. In fact, when Guru asked me to give this, I hesitate because the complexity of the problems facing collectively all the speakers is much bigger than anything that I have faced. But nevertheless, he mentioned complex systems, and I'm going to kind of give a talk trying to address a little bit what I thought was the call of the meeting, the diverse engineering disciplines converge and augment the thinking. So let me start by mentioning two things. One is I'm going to make some reference to the issue of interdisciplinary or multidisciplinary, and I'm going to make some reference to academic silos. All of these disciplines, engineering, natural science, mathematics, at the very root, the epistemology is different for all of them. But as I said, I was humbled by seeing the magnitude of problems facing collectively the speakers in this conference. Out of everything that I could pick, I am using this figure just to show I can imagine anything more complex than this, the problems of feeding 10 billion people within planetary terrestrial boundaries. And these are some of the words that have been used. I poke in and out of the presentations. And there were lots of talks leading to this symposium today. And I'm going to take more or less the same attitude as Norman Augustine talked in summarizing 27 talks in there, which is he talked about engineering 3.0. I'm going to kind of talk about complex systems in general, but starting way, way below. But first, just to indicate how humble I am about this topic, I live very close to the lake in Chicago, and you know, Chicago did something that was never done or was done very few times in the history of humanity: reverse the course of a river, alter the ecology of the Great Lakes. And this is obviously a problem affected by climate change, but this is so much smaller than the problems that we are facing here. But the point is, we have no clue if the level of the Great Lakes is going to go up or down. Sometimes, you know, if something is going up, that's at least something. In this case, we are clueless if it's going up or down. So these are the things that I decided I will talk about. I will talk a little bit about the origins of complex systems, the difference between complex and complicated, emergence, networks, complementarity, which may be kind of new to some people, something about what is needed, organizations, and then barriers, and the wrap-up. Now, let me start by acknowledging 2 points. One is the criticisms of the field of complexity. In '95, when the beginnings of the Santa Fe Institute, this fellow John Horgan wrote a paper highly critical of the field because the field promised too much. It was from complexity to perplexity. And then more recently, collecting 40 definitions on Seth Lloyd from MIT, he said, can you study something if you are not sure exactly what it is? Well, I'm going to give you an answer to this question at the end. But I want to acknowledge something that has to do with limitations of vocabulary. Complex, the way that I will use it in the talk, is in terms of the technical meaning that most people who work in complex systems use. But there are many things that are complex, which are probably outside the realm of what people study in complex systems. And the word complex in everyday use cannot be avoided mixing up with the technical meaning. So I hope you forgive me for that. Now, if you want to have a starting point for complexity, you can pick either one of these two people, Phil Anderson or von Neumann. They were both at Princeton. Anderson wrote a very influential paper, More is Different. And von Neumann, who can be connected with models, cellular automata, even games, is also at the root of this because cellular automata are at the root of complex systems. Now, those are the three things that link complex systems. Hyper-realistic models being the models in which you can more or less substitute reality by a computer program as flying an airplane. And when you want to test models outside the boundaries of what things you put in the model, you play games with them. And the next person that I will mention kind of links these models and games because he was at the Rand Institute for a while. And this person is Thomas Schelling, who won the Nobel Prize of Economics in 2005. And he wrote a book. And when I heard about this book, the title kind of says it all, from micro motives to macro behavior. And he made the observation, this is before you could simulate this with computers, he was flipping coins, that behavior sometimes in the aggregate is more than the simple summation of individual behaviors, and how sometimes it's very hard to infer from the results the individual intentions of the group. So one of the things that Thomas Schelling did, especially in this book, was modeling segregation in a city. So the city was a checkerboard. There were two classes of people, let's say blue people and orange people. You can put an equal number of both of them, and you need to leave empty spaces since the people need to move. And in this case, let's say 90% of the blocks are occupied and the key variable here, the key variable, is how tolerant these people are. So each person has 8 neighbors, and everybody will be happy if half of the neighbors are of the same color. So in here you put all the people in a checkerboard. Here is one of the realizations, and you can see, for example, this blue person is unhappy because there is no one next to him and 2 orange people. So all the crosses represent unhappy people. Now they have to start moving, move more, and now everybody's happy. But look how segregated this is. This is the surprise that Thomas Schelling had, that from individual sort of components, you couldn't deduce the aggregate of the system. So complex systems appear in many, many ways. For example, this is something close to me since I have done work in nonlinear dynamics and chaos and complexity. And when these little particles are bounced up and down, they form all of these phases that you couldn't possibly have imagined that this will happen by studying just one of these little balls. The same thing, you can study a fish to death and you'll never come up with a conclusion that they will aggregate in schools of fish, or flocks of birds, in this case starlings, or that termites will be in mounds like this. But the explanation of these things can be very simple. So the 2D algorithm that can produce something like mounds is random walks, grab a piece, if you hit another piece of wood, you leave it there and repeat. And eventually you get something like this. So why is this important? Because a key tenet in physics was that understanding of the building blocks gives an understanding of the system. Reductionism penetrated all science, even social sciences, but marching up in scales can create surprises. In fact, it doesn't take much. 3 bodies interacting with each other can produce chaos. But the problem with this is that complex systems were perceived to be, again, reductionism. That is not so, since you use the building blocks to build things. But let me tell you what the connection is with engineering. In engineering, each part is designed, and sometimes, but not always, also always the whole. So, for example, every screw in the building of the 787 has to fit in a place designated for the screw. The pieces do not adapt. All the pieces have to converge from many places. An amazingly complicated design building block in here and supply chain. And every piece is designed to fulfill a function. And everything is designed in one shot. Now, in the internet, if you look at the backbone of the internet and the routers and everything, each piece was designed by us. But how the internet as a whole is, no one had the blueprint, okay? The same thing with power grids, transportation. All of these are examples of complex systems. There are other examples of complex systems in cellular metabolisms, that's nature, and how they interact with man-made components in transportation and epidemics. So the point that I'm trying to make in here is there are systems that are called complicated, like every little gear in a watch fulfills a function. Every piece in a nuclear sub fulfills a function, and if you think that something is going to fail, you back it up. But in complex systems, it's hard to predict where from one of the components what will emerge. So no one has figured out how neurons interacting with each other will produce consciousness. So central to the idea of complex systems, defining the way that I'm defining here, is the concept of emergence. So emergence is that the understanding of a component does not provide an understanding of the wholes. So birds in flocks, individual cities in producing segregations, neurons, consciousness. So the definition of a complex system is something that you recognize by what it does, displays some degree of organization without a blueprint, behavior emerges, and how can be analyzed. you have to attack it as a whole. Decomposing the system does not give a clue of the behavior of the whole. Rich behavior with simple parts. So if you have to summarize in 2 lines about complexities, simple behaviors can produce complex outcomes, and complex outcomes may have simple explanations. Or in this way also, knowing individual components, can you predict consequences? The answer to that is no. And if we know the consequences, could you tell the individual actions? The answer to that is no. So what's the conflict here? The conflict is that the hallmark of complex systems are adaptation, self-organization, and emergence. Engineering is about making things happen, consistency of design, and convergence. So a useful metaphor is to compare engineered systems and biological systems. So engineered systems are complicated. There are blueprints, every part fulfills a function, there are instructions for assembly, there is a guide for repairs, you can diagnose or predict failures. Living systems are complex, they are robust, they fail gracefully, they tolerate imperfect components, they are adaptable within limits, they can learn to solve problems, they are highly contextual. For example, stem cells can take on many functions and they display emergence. So biological systems adapt, engineered systems do not. So engineering has typically dealt with complicated systems as opposed to complex. Is the engineering profession prepared to deal with complex problems? The answer is not yet. Many people are trying, we are trying, but the answer is not yet. So an initial goal when complexity started was to produce a unified theory of complex systems. They came with different names, and the idea was that if you have this theory that encompasses everything, you can produce tools, and the tools attack different problems. In fact, what happened is that there was an interplay between tools and problems, and the tools of complexity that, in my view, are these main 4: nonlinear dynamics, chaos theories within here, statistical mechanics, agent-based models, and network theory. All of these tools, not all of them at the same time, produce branches, so many that no one can put them together. So some people study collective behavior. I put 3 names in most of them: social science, synchronization, epidemics, and so on and so forth. So of those tools, I'm going to pick networks, which are nodes connected by links or sometimes edges. So for example, in the nodes could be genes, and the link would be cross-regulations. Or if it's a social system, persons and the social relationship, or an ecology, species and trophic relations, who eats whom here. So the beginning of complex systems can be traced, networks part, to 2 main papers. One was the Small World Networks by Duncan, Watts, and Strogatz, and then the Scale-Free Networks by Barabasi. And of course, this was Nature, this was Science, what was needed to complete the triad, Proceedings of the National Academy of Science. Another paper saying there are many classes in between, okay? So the emergence of network science, there is a society, there are prizes, awards, there's a large body of work, and there has been a bifurcation due to problems and specific results within classes. So inherent to networks, there are failures, cascade, like an overloaded line in a power grid. Power transmission can lead to blackouts or congestion in a single router, internet collapse. The truth is, many networks are constantly failing, but they work. So let me give you one very simple example. The networks within cellular metabolism. So you have, let's say, 3 species that pass through this metabolite 1, produce 2, and in here you have one very teeny little example of such a network. And let's say that you eliminate 4, what would happen? So what you cannot happen is consumption must be balanced by production. If that's broken, you have to look at what are the consequences, I'll eliminate, and from this, you get something like this. But obviously, you look at things that are much more complicated. A metabolic network can be something like this. and you studied the cascade failure. So for example, in one work that we did, you study how robust the actual network is compared with a null set of a network, something that has basically the same characteristics but is random. Now, networks can connect with other networks. So for example, you can have a sort of a grid which is confined, let's say, to northern Italy. Something fails, but in failing that, produces failure in some nodes of the internet, and that produces further breakdown in power stations in other networks, in this case in Italy. So this was a paper in Nature, and so there are lots of papers about these kinds of things. So what do we know in networks? The possibility of hidden connections, anticipate failures, and so forth. And you have to learn to respect and maximize emergence. So there are big questions, how networks grow, stability, robustness. But let me give you one example of network thinking. So for example, looking for causes in complex systems. In the Atlantic, northern cod fishery, cod were disappearing. So they tried to, it was going down precipitously. They had to find the reason. And finally, the reason was carp seals. Why? Because carp seals is cod is crustaceans. But that's a simple explanation. But if you look at the whole ecosystem on where cod is, carp seals, and crustaceans, it's really impossible to predict based on that simple model what the consequence will be. In fact, for a system of about 9 species, the number of possible ecosystems that we create with binary connectivity is about 10 to the 21, which is more than the number of stars in the universe. That doesn't mean that you cannot understand things. There are many people who have studied various ecosystems that have been mapped in detail, and they scale in similar ways. The other thing in complex systems is that sometimes examining the system in some particular way can alter the system. And this happened with Google Flu. Google searches, could you predict breakouts of flu? But once the papers were out, you discover that they were over-predicting, the system not being independent of the analysis of the system itself. So where are we now and what's needed to move things forward? There are possible lots of branches, but one thing that is inevitable is that the complicated is morphing with complex because we're embedding AI in some of these systems. The other thing that is happening, if you pay attention and you are a sort of reader who pays attention and reads good publications, we are getting like a crash system in complexity because many publications are hiring data journalists. We are more exposed than ever, but we cannot see linkages be outside ourselves. So for example, many things remain hidden from view. It's inevitable that there will be products that will allow us to do the carbon footprint evaluation in our consumption. So where are we and what's needed? What we need is alignment of rationality with intuition. This is a quote attributed to Einstein: the intuitive mind is a sacred gift and the rational mind is a faithful servant. We have created a society that honors the servant and have forgotten the gift. Now, it serves to make the point because of an overlooked concept also associated with complexity. I mentioned these lessons, but one other lesson is that chaos and order are not opposites. So it's important to see the parts and see the whole. Reductionism was everywhere in science. Complementarity stayed within physics, quantum mechanics, but complementarity is the ability of reconcile opposite viewpoints. And this is becoming an essential characteristic of a leader, especially now. Rationality and intuition, creation and analysis, even art and sciences. The ability of seeing the simplicity in the complexity and the complexity in the simplicity, and seeing both at the same time. Now, let me give you one very quick example here, and I know I'm running out of time, of complexity and organizations. And in what way a university like a biological system. So when you look at a any organization, and you look at the top part, you have the CEO, the chief marketing officer, all of those positions stay fixed. And in a large organization, everybody up to the lower level, they don't morph in new positions. However, in a university, this is where departments are, faculty and students, post-tenure, I do not know how this is effectively used, is individual reinvention is possible and desirable. So the university is more like a complex system rather than a complicated system. So by design, classical companies are complex, complicated universities are complex. So complexity can be good, but one needs to be able to deal with uncertainty and ambiguity. And as I said, the role of the leader is to provide conditions for successful emergence. There could be another whole talk about managing complex organization. Now, the main point that I want to make here is that the substantial benefit by incorporation of complex systems, tools, and thinking into existing toolkits and domains. So the barrier to interdisciplinary work is thinking of other disciplines in terms of the outcomes rather than the process. Do not equate outcome with process. You have to understand process. And this goes beyond empathy. This is understanding how people think and how do things. So going back to the question, can you study something if you are not exactly sure what it is? Well, this is my proof in here, okay? So this is work from Amish Kapoor. It's called Leviathan. It was in the Grand Palais in Paris. And if you ask Anish Kapoor why he did this and what he thinks about artists, or if you ask any artist, pick 100 of them, encapsulate the essence of domain in a verb. In science, many people say discovery and technology invention. Art, all artists will never say creation. They will say all of these words: irritate, challenge, reframe, and so on. So things do not have a name when someone is studying something new. Point one. Point two, people have been studying art since the beginning of humanity. There are art historians galore. And if you ask people to define exactly what art is, they cannot define. So the answer to the question, can you start something that you cannot define? The answer definitely is yes. Now, do people become overly enthusiastic in terms of promises? Definitely yes. Every revolution goes too far, okay? So complex systems tools and complex people from complex systems as cross-linkers can lead to the creation of new disciplines. The progress resides in understanding how others' domains think. You have to force yourself to embrace complementarity and hold two ideas that really oppose each other. And my overall conclusion, this revolution may not have fully started yet. Thank you so much. And I'm sorry I ran over a little bit. Thank you, Guru, for inviting me. And thank you all for the opportunity to present some of my views here. Thank you so much.
Julio, thank you very much. This was impressive at many, many scales. Importantly also because you managed to compress 90 PowerPoint slides into 25 minutes. So we have much to learn from that achievement as well. Two things stood out for me. And one, especially when you said how we need to get good at respecting and maximizing emergence. And so productive emergence, of course, that's what you're talking about when it comes to network thinking. And also, how do leaders create conditions for successful emergence? And I think that has broad applicability as well. Mm-hmm. One of our participants also asked a related question on emergence. But my question is, does specialization, early specialization, or some form of disciplinary specialization provide you a platform to better appreciate this kind of network thinking that you have been articulating? So I think we're stuck between starting general and then becoming specialized, or the other way around. So
yeah. So I created an institute, which, by the way, is the only institute in Northwestern that has generated other institutes. For example, synthetic biology emerged from there. And the way that we did this is we organized a series of luncheons and said, if you work in anything connected with complex systems, come on in. But implicit in the come on in was you have to have the curiosity or the ability to connect with people who are doing something that they also call complex systems, but it's not exactly what you're doing. And you may disagree as to how you define terminology. So you need two things. You need people who have expertise in something, go deeply down in something, but they have some ability to connect horizontally with other people, okay? And I think key to that is understanding how is that people formulate questions in different disciplines. For example, if you want something completely different, the way that an artist will formulate the question, how this guy, Anish Kapoor, decided, you got this space, do something in here. How is that he came with that thing? Because it's not like you do that in the spur of the moment. So it's understanding, not equating disciplines with the outcome of what they produce, but rather with the process that they use to think about something. And there are enough people like this, but you just need to collect them. You need to kind of prepare the ground for them to be able to link with each other.
Right, and I think artists would appropriately use the concept of levels of abstraction. How do you successfully perform at all those levels? And one of our earlier speakers, Luis Fresco, also pointed out the importance of making trade-offs competently at those different levels. I invite our participants to send their questions for Julio, and I'll pick and choose what's possible to be asked in the next 10 minutes or so. Please use the chat function. Julio, I do have another question though. We started off the event today by acknowledging how the COVID pandemic has basically weakened the infrastructure, intellectually speaking, financially, and especially on food, agriculture, nutrition, and so forth. So we are living in fairly distributed fashion, as confined fashion, rather. So how do you see this kind of complexity awareness, network systems thinking, to be achieved in a dispersed environment, assuming this is a new modality of life we are imposing on ourselves going forward?
Yeah, so let me step back and answer one question that I will ask myself. In any organization now, given, for example, my own institution, you are dealing with so many pressing problems that to take the here and now, that you can say, all of you deal with the here and now. But if you don't protect a group of people to think about the future, okay, you are going to be stuck in solving the immediate challenge, which are so many now. So the question is, you need to sort of carve enough time and space for people who can. And this is the problem now, is there are no random connectivity now. If you don't schedule something, doesn't happen. You have to schedule, you have to be intentional as to, which is basically what you are doing in this conference. You curated a group of people that you think have some common interest, and what connections will emerge out of the collection of people that you curated in here, you cannot predict beforehand. But just by assembling them, some of those connections will emerge. Some people will email each other and say, by the way, I was really interested in what you said about that. I never thought about that. So it's basically doing at all scales what you are attempting to do here in this conference. That's my view.
Very good. Thank you, Julio. There's a question on the chat, and I'll generalize that from Charlie Messina. Of course, outstanding talk here. And the individual has asked if it's time to bring emergence engineering to agricultural and biological engineering curricula. I think I can say the answer on your behalf, yes. But the question now for you is maybe to build on your experiences with the Complexity Institute at Northwestern, and maybe even share some war stories with us, how you managed to incorporate those within your engineering school.
Yeah, I mean, the challenge is, as I said, we had talks from faculty to faculty. luncheons, no pressure. Someone asked me about Bayesian statistics here. So we invited lots of people who are in economics doing games, game theory. And I wouldn't say that it was hugely successful because we invited people from math, physics, and so on. Eventually, and this is what I said, eventually at the beginning of the Santa Fe Institute, people thought, maybe we come up with one theory that will encompass all of this. And eventually what happens is people who are doing networks and have an inclination to study social systems, like for example, a system that was studied, really interesting, the composition of teams. What teams produce the best results? Mm-hmm. And one example that I found fascinating, because there are teams recorded since the beginning of this industry, and how successful the outcome of these teams was production of musicals in Broadway, okay? And even because every Broadway musical has about 5 people, a librettist, a choreographer, a producer, whatever. And eventually, just from that, people aggregated and a group was formed on a computational social science. The Broadway thing was like the excuse. And then those people kind of formed their own little clubs and this and that. And they move away from the rest, from the people who are doing biology, for example, and synthetic bio. I made reference in there about combining pieces, producing outcome, but some of the pieces morphing into, depending on context, like stem cells. So eventually things will bifurcate, and if you want to keep the level of exchange of ideas flowing, you need once in a while to bring one person from one of those groups and talk to the other people in the other groups. Otherwise, the whole thing diverges and you can never capture the center again.
Yeah, and to use the metaphors from food and agriculture here, and that seems like a very organic way of bringing diversity and inclusion deliberately and seed new possibilities, rather. We have a good question here.
So by the way, so the point is, if you don't watch out, all the ideas, the best way to get a good idea is to get lots of ideas. Okay, Linus Pauling said this, but you want ideas that are different from each other. And eventually, if you will get lots of ideas from a set of people who start thinking alike, the ideas are not going to be very rich. You want diversity of ideas. And by that, you need to bring different people. You need to engineer the teams behind the ideas. Yeah. So this is why meetings like this exist, is to engineer ideas.
And thanks to you, we brought in Anish Kapoor into a conversation with agricultural scientists here. So that's good. In here, Julio, I think you can go in any different direction here with this. Question is, I was wondering, Dr. Utina's thoughts on suggestions for junior researchers, where to begin identifying ideas that will have a transformative effect and also produce viable research and teaching pathways in a complex system such as ours.
So I'll tell you one thing that I created this institute and I was the director of it initially. And we had positions that, postdoctoral positions, paid, but this person had to come up with a project that will link people from 2 different schools. Maybe the project was generated by people in those schools saying, by the way, you are doing this, I'm doing this, how about if we do this and we can get a person to work on that? So it could be that the person generated that, but you are looking at the landscape of all the things that are going on there. You have the state of the system at time t, and you want obviously to expand the set and produce the next thing that it breaks the boundaries of the set. That's what I like the term breakthrough, rather than because it breaks through the knowledge that exist in this set. And you have to be curious. I mean, I believe you can teach almost anything, including how to be more creative. The thing that is almost impossible to teach, in my view, is how to be curious. That's impossible. But if you want good ideas, you have to be curious.
Julio, on that high note, let's conclude our conversation. And thank you very much. You put in a lot of effort into the presentation, and you have helped expand our imaginations here. I think as a general purpose concept platform, we can go in many different trajectories, including especially the existential topic that we're talking about, food, agriculture, and nutrition. Thank you once again on behalf of the National.
Thank you all for the opportunity. Thank you.
Very good.
Bye, Guru. Bye-bye.